Well, here's a different twist on a problem using implicit differentiation. We're to find y prime, which is dy over dx, isn't it? If e to the y plus y is equal to plus x is equal to 2. So here's specifically an example where we wouldn't be able to solve this for y. I don't think that I could solve it for y. It'd be a lot of work if I was able to at all. But we can still find y prime. And of course, remember the way we do that is that we're going to do it implicitly, so we take the derivative of both sides. Okay, so we have the derivative with respect to x of the left side, which is e to the y power plus y plus x, is equal to the derivative of the right side with respect to x. And of course, the right side is just 2. So we break the left side into 3 derivatives, that is, the derivative of e to the y with respect to x, plus the derivative of y with respect to x, plus the derivative of x with respect to x, and equal the derivative of 2 with respect to x, which is just 0. Now, before we do this next step, I want to remind you we had the chain rule for exponential functions. For instance, here's what I'm getting at. If we were ever asked to find the derivative of, say, e to a power like 3x, then we knew that we got e to the same power, and then we had to multiply with the derivative of the power, didn't we? In this case, that result would just be a 3. Okay. And more generally, what we decided is the chain rule applied to e to powers is that if we had e to a power that was an expression in x, then we got e to that same power, and then we multiplied that with the derivative of the power, didn't we? Okay, and so what I'm trying to remind you of here is that when the power on e is not just x alone, if we're taking the derivative with respect to x, then we have to use the chain rule. So derivative of e to the y, it's not e to the x, it's e to the y. With respect to x, well, it will be e to the same power, but then we have to multiply with the derivative of the power itself. And so I'm going to represent the derivative of the power, the derivative of y as just y prime. Okay, now in a similar fashion here, we're taking the derivative of y with respect to x in the second derivative. And we could call that dy over dx, or we could call it y prime. And I'm choosing to call it y prime, being consistent with what we've got. And then plus. Okay, well, in this case, what we have is the derivative of x with respect to x. That's just a normal derivative, and that gives 1, doesn't it? Okay, so we've got an equation now that involves these y primes. So we have to solve the equation for y prime. That's what we've got to do. That's what we want to know, is what is y prime. So the way we do that, let me kind of let's just put some other stuff here. This is kind of an idea of how we might solve an equation, and I hope that you get an idea of how we would do this more generally. We're looking for y prime, so everything else I'm just going to think of is like a constant. So this would be similar to having 5y prime plus y prime plus 1 equals 0. I'm just trying to keep things from not being so confusing here. And so if we were trying to solve for this thing called y prime, we would get rid of the 1 on both sides. I mean, on the right side, on the left side, we'd subtract 1. And then we'd say, oh, we've got 5 of these y primes and 1 of these y primes, so we've got 6 of them all together, don't we? See, we've got 6 of them all together there. And then we would divide both sides by 6, and we'd get y prime is equal to negative 1 over 6. Now, of course, that's not what we're doing here, but I'm wanting you to think in those terms, is that when we look at this equation, there's 2 pieces that involve y prime. And we want to keep those together because we want to combine those like we combine 5y prime and 1y prime. But with the plus 1 we want to get rid of, and so we're going to subtract 1 on both sides, and then our equation will look like e to the y times y prime plus y prime is equal to negative 1. Now, in this case, we don't have coefficients that we can add, but we do have a coefficient of y prime in the front that's e to the y, and the coefficient of y prime in the second one is just 1. And so it's kind of like adding the 5 and the 1. We'd be adding the e to the y and the 1, wouldn't we? But more generally, these two terms that are on the same side both involve y prime. That's why we want y primes together. And so y prime is a common factor, isn't it? And if it's a common factor, we can factor a y prime out. So that's all I've done is I've factored y prime out to the right side. And so that's like the 5 plus 1 for the new coefficient. That's the new coefficient of y prime. And we need to divide it out, don't we? We need to divide on both sides by that y prime. By that coefficient of y prime. So we're dividing on both sides by e to the y plus 1, and on the left side that just leaves y prime, and on the right side it leaves the fraction negative 1 divided by e to the y plus 1. So there's our answer to this third example. Okay, I think I'll do the fourth example on a new page. Okay, you can see in this example 4, it looks almost identical to example 3, except the exponent that's on E is xy, x times y, instead of just y. So this is going to require yet a new twist. So we're going to start out by finding the derivative of both sides. Okay, we're looking for y prime, which is dy dx, isn't it? So we're going to take the derivative of both sides. Now, when we take the derivative of the left side, it's actually going to end up being 3 derivatives. So let's go ahead and streamline a bit and just go ahead and write that out. And of course, on the right side, the derivative of 2 is going to be 0, so that we streamlined a bit there. Okay, now here we've got a new situation. Well, earlier we said simply this, that the derivative of e to the power, and this is as simple as it is, derivative of e to the power is e to that power, then we have to say times the derivative of the power itself. And in this case, the derivative of the power itself is xy. So we have to find the derivative of xy. And then in the second derivative, we've got derivative of y with respect to x, which is just y prime. And in the third derivative, we have the derivative of x with respect to x, which is just 1. Again, that's a normal derivative. But what I'd like to do is I'd like to come over here to the side and work on this one derivative, that is the derivative of xy with respect to x. Now, to do this derivative, and we're going to need to use the product rule. See, we have the product of x and a function y that we don't really know what y is, but it's a function of x. So the product rule is going to have to be used here. And I kind of don't have much room, so I'm going to come down here and say, okay, when we're using the product rule, we say first function, that's x, times derivative of the second function. Well, the second function is y. And then we reverse that, don't we? We say plus second function, which is y in this case, times derivative of the first function, and the first function is x in this case. And remember, we're taking the derivative with respect to x. So what we have here is x, and derivative of y with respect to x, we've been calling y prime in this problem. And then over here, we have the y, but the derivative of x with respect to x is just 1, isn't it? So this ends up being xy prime plus y. Now remember, that's this derivative. And so we have a place to put it in. Right here is what we just found, isn't it? So we have to be careful about the way we do this. Okay? We have an e to the power xy And then we have the derivative, which ends up being xy prime plus y. That is, we have derivative of xy, which is xy prime plus y. And then we have the plus y prime that's out here, and the plus 1 that's out here, and the equals 0. And let me remind you, now that we've implicitly found derivatives, we need to solve for, we're trying to find derivative of y with respect to x, but in the form, we're calling it y prime, aren't we? So we need to solve for y prime. Well, there's a lot of stuff involving y prime, and so I guess here's what I'm wanting to do once again. I want you to think this way. And I won't do this all the time, but we're looking for this thing y prime. Everything that's not a y prime is like a constant in the equation. So let me just replace e to the power xy with a number so it'll make more sense to us. And let me replace 2 with just a number. We're solving for y prime, so it'd be like a 2y prime there, and then y is not what we're solving for. We're solving for y prime, so let's put a number in that place. And then we have a y prime, we are solving for that, plus 1 equals 0. And so I had asked you here, if we were solving for y prime, the first thing we would do is multiply that 5 out, wouldn't we? We'd say 5 times 2y prime, that'd be 10y prime, and then plus a 15, and then plus y prime and plus 1 equals 0. And then we can combine the things on this left side that we have, but ultimately what we want to do, let me just kind of throw it out this way, we want to get the things that involve y prime on one side and the things that don't involve y prime on the other side. Okay? And that's the way we would approach it. And then we'd combine the y primes. 10 plus 1 is 11y prime. And of course over here we could say negative 16. And then we'd be on our way, wouldn't we? Well, I did all of that so that we would know how to approach this. We need to expand and gather things up so that we have y primes only on one side and things that don't involve y prime on the other. But the first thing we're going to be required to do is multiply out this e to the xy power. So we'll have e to the xy power times x times y prime plus e to the xy power times y. Then plus y prime and then plus 1 equals 0. So there are 2 terms that involve y prime. Everything else we need to the other side of the equation. So we'll leave these 2 terms alone, and we'll subtract 1, and we'll subtract e to the power xy times y. Now, normally we'd actually write this y in front of that e power, e to a power, so I'll do that in the next step. Now, we can't add the coefficients so easily here of y prime. Remember, we're solving for y prime, but it ends up being both terms have y prime. That's the reason we want only things with y prime on the left side, because now it's a common factor. So that's the whole purpose that we left the y prime stuff on one side. And so since that's a common factor, we can factor it out. If you factor y prime out, it would look like that, wouldn't it? Now I'm going to do a couple of things here. I'm going to rewrite this as -1 minus and put the y in front of the e to the power. And I'm going to do the same thing here. I'm going to put that x in front. This is an extra step, I realize, but it's a little cleaner this way. Okay. Now, we're solving for y prime, and so this stuff in the parentheses on the left side is like our 11 over here, isn't it? We need to divide that coefficient out. And so we'll have, I'll just show it. I'm going to divide out that x, e to the xy plus 1. See, we're dividing that out so we can cancel. That means we've got to divide the other side by the same thing, don't we? Okay, well, when we do that, then we're left with y prime is equal to negative 1 minus y times e to the xy over x e to the xy, and I apologize that y is part of the exponent there and didn't look that way, plus 1. Now, there's nothing wrong with that answer. That's perfectly acceptable. I am noticing that we have a negative 1 that is in front of, in the numerator. That negative 1 could actually be factored out. See, we could write this as negative of 1 plus y e to the power xy over x times e to the power xy plus 1. And then that kind of gets me to thinking that I could rewrite this a little differently even. I could put that negative that's in front of the parentheses in front of the whole fraction. And then that numerator, 1 plus y times e to a power, I could kind of make it more symmetric with the bottom, and I could write it as y e to the power xy plus 1 over x times e to the power xy plus 1. And then they would look more similar, wouldn't they? This answer is certainly accurate and correct. This might be an answer that you would see in the back of a book, or maybe in my math lab is the answer that they might give. Well, we'll now move to I think I have one last problem that I'd like to demonstrate for you, unless you've got some others that you'd like me to consider.